Okay, so last time we defined what is an abstract Lie algebra, and one particular example of an abstract Lie algebra was the following. If you start with just an associative Lie algebra, well, associative algebra. Lie algebra is, of course, not associative. Depends how you put the brackets in the. If you have 3 elements, it depends on how you put the brackets, right? So if you start with associative one, then derivations of A, which are all linear transformations, D, all linear transformations such that they satisfy Jacobi identity. So D of AB is D of AB plus AD of B is a Lie algebra which, as it is, might be not finite dimensional. One particular case of this is when A is C infinity of x, all smooth functions on some smooth manifold x. So x is smooth manifold. And C infinity of x is smooth functions. Of course, you can multiply it, these functions pointwise, and this makes it an associative algebra. And then derivations of C infinity of x, this by definition are all vector fields on x. And vector fields with respect to taking a commutator gives you Lie algebra. So we, for the first half of this lecture, will be interested in this Lie algebra because if you put, so because of the following construction, so suppose that now you have Lie group G, and it acts on a smooth manifold X. And so this is Lie group action. And consider a map. So this is some action that we denote as alpha. And consider the following map, which we call V alpha. This is map from G, which is tangent Lie algebra of the group G, to vector fields on X. And it is defined as follows. So actually alpha is a map from G times X to X, right? This is our action, and for a pair element of a group and a point in the manifold, you have a corresponding point in the manifold which is given by G acting on X. Right. Then we also had this map alpha X for some fixed point X in X. And this was mapped from G to G, which was defined as follows. So we had you take an element G in here, and the result of the image of this map is just sorry, from G to X. Then the result is G times X. Right, for some fixed X. All right, so all this we need to recall to define this V alpha, right? So V alpha works as follows. It's an element of G, small, and gives me a field V xi, which is defined, so where V xi is defined as follows. So I need to take its value at some point, and this will be then tangent vector of x with respect to this point. And by definition, this is differential of alpha x, right, applied to psi. So differential of alpha x, right, so of alpha x is like that. Differential, it's a map from G, well, and where is this P here? This P is yes, so V xi of P, and this P should be a point in X, right? Right, and so this P sits in here, and differential is at identity. So differential at identity is a map from G to tangent space at the tangent space at X, right? Because this should map tangent space at identity to the tangent space of alpha x of identity, right? But alpha x of identity is exactly x. So we have this, right? So therefore, if I take psi, which is an element of G, apply d alpha p to it, I will get an element in Tpx, which is exactly the value of a vector field at the point P. That's exactly where this object should live. So this is a really correct definition. All objects live in sets where they should live. Okay, so why this is interesting? So we are going to realize Li algebra as a Li algebra of left-invariant vector fields on G, right? But before we can work in greater generality, take not smooth, like any smooth manifold, maybe not X, and consider this map, and the proposition that we would like to prove is that the map V alpha, which is actually linear map by definition, but we would like to see that this is homomorphism of Lie algebras. well, we defined what is homomorphism of tangent Lie algebras, and homomorphism of Lie algebras is can be defined in the same way. Just some linear map, right, that respects the Lie bracket. So let's prove this. Okay, so let us fix phi. It is again a centered chart of G at E. Of G at E, right? So meaning that it is a map from U to K and being dimension of G, and E lives in here, and U lives in G. And phi of E is 0. So suppose that we have a chart around identity like this. Then let me fix like a basis, like standard basis. Fix notation for standard basis in Kn. So E1 dot 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 En. So let it be standard basis in Kn, meaning that Ei, right, is this 0, 0, 0, and 1 on ith place, and again zeros. Then let me more or less the proof of this proposition is straightforward check, right? So just in coordinates. This is what we are going to do, just accurately. So let's see what else do we need. We need this curve with tangent space corresponding to so curves gamma I of t. It just defines as follows: phi of t ei. And well, phi is well, the chart is usually this way, right? But as I wrote it here, I actually would like this to be phi inverse, right? I would like to go from some open set of Kn to G, right? Okay. So this really lives in Kn, and I map it. So this is an element in G, and this is a smooth curve in G for each I from 1 to n. And then I can consider psi I, which is a tangent vector tangent to this curve at 0 for each I. Then psi 1 is psi 2 and so on, psi n. This gives me basis in G, which is tangent space at identity to G. And well, I have V psi I, right? So let me take V psi I and let me understand how it acts on some function f, right? So actually, this is derivation, right? That acts on some function f as follows. This gives me another function, which at point P is given as follows. It is the derivative with respect to parameter t of f of the element of g, which is phi of t ei. T is this parameter with respect to which I differentiate. And this is an element of g. F is a function, smooth function on x. So therefore, it eats elements of x, so I need to act on P. This gives me an element of x, f acts on this element, and this becomes a function of t, well, which is really like a function from field to field, right? From R to R or C to C, depending on our situation. Okay, and well, I should close the bracket here. Two brackets actually, two parentheses, and take t equals to 0. So this is exact formula what vector field v psi I by our definition. This is the definition. If you go through the definition accurately, this is exactly what it means. Right, and this dot is exactly the same dot as I use here. It is our action. Okay. So so you act on a point by very small element corresponding to this very small element of g, which looks into direction which is given in these coordinates by ith standard element of the basis. So that's what's going on, and this is our v psi I. Okay, and also another thing technical that we're going to use is that, okay, if I take one element of g like this, multiply by another element of g like this, if x and I and xj are small enough, I can write this as a phi of something. And what is this something if I expand it as a Taylor series of xi and xj? This will become this xi ei plus xj ej plus some bilinear form gamma of x I and xj right. So what is this gamma and plus terms of degree greater or equal than 3 in xi and xj. So this is really the same as our computation for group commutator in coordinates, and we expanded it as a series in coordinates of the initial elements that we put in the group commutator. So this is really the same computation, but not for group commutator, but just for multiplication. So in multiplication, you will have linear terms, which are like this, and then and then a bilinear term, and then terms of degree greater or equal than xi and xj. This can be seen in exact same way as we did it for group commutator. Moreover, if I write down gamma, it's bilinear term, something bilinear in xi and xj, and moreover, it should be a vector, right? Because phi is a vector. So this is vector, this is a vector, this should be a vector. So this is expanded in our basis EA will be something like Q I J X I X J. Here sum over A from 1 to n. And no sum over I and j because we have dependence on them on the left. Sorry, this is not Q, but rather gamma. Right? So actually this is just defining so gamma is something of this form with some coefficients gamma ij. And it should be index A in gamma. Right. So actually, if you remember, we had this like the group commutator, right, of two things, and we had like the quadratic form Q there of two elements G and H, right? Actually, it is true that Q. So this is quadratic. So we had G H group commutator is this, right? So this is some recall from previous lectures, plus terms of degree greater or equal than 3 of G, in G and H. So there's a connection, of course. It's easy to see that there's connection between this Q and this gamma. Actually, if I can rewrite Q, well, I can put so suppose that we have some coordinates, right, of G and H, right? X bar are coordinates of G, Y bar coordinates of H. And this is sum over Q I J A, right? And EA. This is also vector in Kn, so therefore its expansion in basis will be like this. And then Xi, Yj, where X bar, well, here maybe I should keep G bar and H bar, so G bar is X1, Xn, H bar is Y1, Yn. So if we define coefficients like this of Q, then there's connection actually between gamma and Q, which is the following. Qija is gamma ij A minus gamma ji A. Well, this is actually some, so this is, I leave as an exercise in, playing with Taylor series. You need to compare, you need to compute Taylor series of this in two different ways. And then you'll get this. So this is exercise. and which means that actually if I take now commutator psi I and psi j, again, just unwind all the definition of this bracket. Right, this is exactly what is d phi, right? Phi is our chart, d phi inversada of EI is exactly this thing, right? And so therefore, the formula of the bracket of psi I and psi j, which are elements in G, is this. It is sum over A of, so since I should take Qij, we already had this formula on the previous lecture, psi A but because of this, it is actually sum over A of gamma ij A minus gamma ji A times psi A Okay, all this we need. So what are we proving? We are proving that V alpha, right, is a homomorphism of Lie algebras. And V alpha takes an element psi and gives me a V psi that, well, in particular psi I gives me V psi I. It's linear, so it's okay just to prove that it's homomorphism on a basis. And V psi works as follows, right? So without loss of generality, we actually can check the following thing. That, okay, I take V psi 1 and V psi 2. These are images of psi 1 and psi 2 under the map V alpha, which we checked that it is homomorphism. Take the bracket. So these are vector fields, and bracket just commutator of vector fields. And commutator of vector fields is again vector field, because commutator of two derivations is again a derivation. And we need to check whether this is equal to V of the commutator of psi 1, not of commutator, of Lie bracket of psi 1 and psi 2. So this is Lie bracket in G, and this is Lie bracket in vec X, right? Lie bracket in vec X is actually commutator, and this is just some abstract thing. Okay, so let's do this. So we are going to take left-hand side and apply it to some function f from C infinity of x. So I take the commutator of vector fields, V psi 1, V psi 2, it's another vector field. I apply it to f, get another function, which value at p is computed as follows. So, well, it's just a commutator. So I apply first V psi 2 to f, and then apply V psi 1 to f. And then minus the same when I replace psi 1 and psi 2, and I use this line to expand all that. So what do I get? I get the following. So it is derivative with respect to parameter s, at s equals 0. Derivative with respect to parameter t, at t equals 0. Of the following thing, f of phi of t e1 phi of s e2, so applied to p. And then, so again, so first I apply psi2, right? Psi2 corresponds to E2, so I apply it and take derivative with respect to s and put s equals to 0. Then I apply psi1, right? It means that to this point I apply the action of this element of G, right, as written over there. Now, but now my new P is this thing, right? And well, and then apply the derivation with respect to S. So, so I move little bit the direction of E2, then move little bit to the direction of E1, and differentiate with respect to both parameters corresponding to movement in this direction and this direction. And then I subtract the same thing, but with E1 replaced with E2, and S replaced with T. Well, doesn't really matter, right? Well, the same thing with so this doesn't really matter with what are the names of parameters. The thing is that first I will get something with E1 and then with E2. Okay, so this is what I need to compute. Now, so I have, because this is an action, application of this and then application of this is the same as I take multiplication in the group first and then I apply it to P. So this is actually left action we're talking about, right? So by default, all our actions are left. So therefore, it is actually multiplication of these two acting on P. But how to deal with multiplication, we know. This is how, right? So I actually can rewrite it. Maybe let me leave this thing. What do I have then? I have then, so I continue, right? So I continue this calculation. And this calculation, so I will have d over ds at s equals 0, d over dt at t equals 0. F of phi, so multiplication, instead of multiplication, I get this guy, right? So it will be phi of t e1 plus s e2 plus sum over a qa 1 2 t s e a. And then plus all other terms that we don't care about. And another parenthesis, which is this one. And then I need to, well, apply this to P, right? I need to apply this to P and put and close another parenthesis. So here I just use this. And minus the same with 1 replaced with 2. Okay, so let me introduce the following notation. F with index phi is just is just the following, right? It is a map from Kn to C. And so I fix P, right? So and then I compose F. So I take F of phi of something from Kn, right? Acted on P. So this is just a notation, and F is my map that I chose here, smooth map. Then what I get, so I need to compute this. So let us recall, I don't know what is calculus 2 in US universities, right? So it's a second derivative. So we need to apply what is called chain rule, right? So chain rule will, according to chain rule, I will need here the derivative with respect to, so let's see, when I differentiate with respect to s and then with respect to t, right, only, and then put s and t equals to 0, only this quadratic term will play the role, right, because these linear terms will be killed after second differentiation. This, after two differentiations, will have s and t in them, and if I put s and t equals 0, they will be gone, right? Well, after chain rule, this will be all outside of f, right? So what I have actually in chain rule is I should look at this term, right? Only this term will give me something which appear in the result, right? And well, you see that, well, this is a function of n variables, right? And f of phi of x times ea means that I put x in eighth variable, right? Well, long story short, I tried to explain it as much as I could. Maybe a formula, just explicit formula, will make it better. So this is the same as sum over a of d over dx a f of phi of 0. So this is just chain. First factor in chain rule, and second factor coming from differentiating what's inside, right? And what is inside will be just Q1, 2, A. And this is sum over A. So this is what chain rule for this term says. Sorry, not Q here, because we agreed that it should be gamma. So this is just gamma, and this is gamma. And from the second term, I will get gamma to 1, A. gamma to 1a. And well, so this is differentiation with respect to xa when I look, so actually at f of phi, right? Here f of phi is a function of x1, x2, and so on, xn as follows. It's just as f phi is a function here of x1, e1, x2, e2, and so on. Okay, so we started with this and ended up with this one. So okay, I can continue. Right, and we need to prove that this action of f is the same as action of this on f. Okay, let's see. What do we get here? So this actually is the same in this notation that I introduced. So first of all, again, let me indicate that this is just application of what's called chain rule. Chain rule. Or the rule of differentiating composite function. Right? So this is one function, inside is this one. Okay. So this, I continue. And what is this thing is actually V, just remembering this. This is the same as V psi A. Just compare. Apply to F at P. Only this factor. So this will be sum over A gamma 1 to A minus gamma to 1 A V psi A apply to F at P. But sum over A with this coefficient of psi A is exactly the commutator of psi I with psi j. Right? So here I put I equals 1, j equals 2, and psi goes to v psi is linear map. So therefore, by formula star, this is the same as v psi 1 psi 2 applied to f at p. And okay, we're lucky now that we started this, make all the computation, and you see where we get. So this is exactly what we needed to check. That our map from psi to v psi is a V group homomorphism. So it maps bracket to bracket. Okay. And this was in generality where X is any smooth manifold and alpha is any smooth action of a Lie group on a manifold. So now let me consider one particular action of G on itself from the right. To make it left action, I need to twist it with taking inverse. So consider the following thing. G acts on G, so some particular alpha. So let's take now some particular alpha. So my alpha, which is from G times G to G, works as this. So G acts on H as, so I take H, multiply by G from the right, and take inverse. So I take inverse so that this inverse is necessary for that to be what is called left action, meaning that G1 action on, so I need this to happen, is G2, G1 acting on H, right? This inverse is necessary for this condition, which is condition for left action. If I erase this inverse, then I should put here G1, G2 in different order, which it means that this was called right action. But since all our formulas was for left action, so let's put this here. Okay. And let us prove the following proposition. That image of our map V alpha is, remember it, V alpha went from the Li algebra to vector fields, right? And in this case, the vector, so my X is G itself. So these are vector fields on G, but I claim that image of V alpha is not all the vector fields on G, but left invariant. Namely, these are all vector fields such that the induced by left action map, which is well, which is pullback here, I believe, of V. I will discuss what it is V again. So this is a map from vector fields to vector fields, right? Well, this is not pullback, this is push forward actually. So this definition, so now what is, question is what is this map LG star? Actually, if I have diffeomorphism F from X to Y, this F is LG in this particular case. So suppose this is diffeomorphism. And X and Y are two smooth varieties, smooth manifolds. Then, well, I can define push forward of a vector field F with lower star, which is map from vector fields on X to vector fields on Y. So how does it work? F star applied to V, it's another vector field in here. I compute its value at point P. P is a point in Y. Right. So P is a point in Y. It's diffio. Therefore, well, we need a diffio in order to actually to define F star, right? Because then I can write the following formula. So it is, I take P, map it back to X. So P is a point in Y. I map it back to X. Then I can consider V at this point, right? V is a vector field on X, so therefore this is tangent vector at point F inverse of P. And then I consider differential of F applied to here. At what point? F inverse of P. So this is just definition. And in this particular case, we take F to be LG and take V vector field on L, define another vector field, LG star, but it happens that we chose such that the new one coincides with the old one. And such vector fields are called left-invariant vector fields. And I claim in this proposition that image of V alpha is exactly left-invariant vector fields on G. So let's prove this. Proof of proposition. Well, okay, so we need to take V psi for some psi in G and prove that it is left invariant. So, and also let me consider any element G of the group. This is Gothic G, this is just usual G to distinguish. And I need to consider push forward LG star. And I would like to see at some point, right, at some point, and the point should be on G, so at some point H. H is another element in G. So I would like to see that it is exactly V psi of H, right? So, right. So actually, this is a vector in a tangent space at H, at point H of G. How is it defined? We use this, right? So we have that this is D LG applied to the vector V psi at the point G inverse H. So I take inverse, consider this, and then apply differential of G. Right? Okay. Only, yes, okay. Differential at what point, so the LG, that at what point you can compute yourself, right? This F inverse of P. It doesn't really matter at this stage. So, okay. Now let me introduce gamma of t. It's a curve. Curve on G such that its corresponding tangent vector to this curve at 0 coincides with this psi that I chose at the beginning. Then I can continue this computation. This will be, so what do I need? I need to apply DLG to this, all right? And I need to recall what is an action. So what I have this point, right? What is the definition of xi? It's a vector field at this point, which at this point gives me a very, very small vector, like very, very small transformation, right? With respect to my action that I chose here, in the direction which is given by xi, right? So I should take gamma, right? Very, very small transformation is given by this curve with this tangent, with the tangent vector corresponding to psi. So I should take this gamma of t with small t, multiply this point by gamma from the right and take inverse. This is exactly how my action works. So gamma inverse. So this is a new curve, right? And I should take tangent vector to this curve and then apply DLG to this. So this is at 0. When I apply DLG to it, this will be, well, I just need to take this curve, multiply by g from the left, and then again consider its derivative at 0. When I multiply by g from the left, I cancel with this g inverse, so I get h gamma inverse at 0, right? But again, this is just the same as considering v psi at point h, right? Because, well, again, how do you, so this is continuation of this computation, so how do you define this? Again, you take this point h, consider very, very small deformation which is given in the direction given by xi, which is our curve for small t, multiply, an action is given by multiplication from the right and taking inverse. And then considering very small deformation in the sense that I taken derivative, right? So this is it, right? So I started with this thing and prove that actually this is the same as initial vector field vxi at the same point h. So therefore, image of v alpha is inside left-invariant vector fields in G. We need another inclusion, right? So conversely, so the other inclusion so let me consider vector v, which is left, well, this is vector field, which is left invariant. And let me denote, take by xi to be its minus its value at identity. So I have to put minus here for some technical reason, because again, in my action I have this inverse here. Very well. Then what? Then let me consider V at some point H. By left invariance, this is the same as L H star V at point H. Then I write definition of what is LH star. This will be just DLH V of H inverse H. This is just all definition. But H inverse H is E. V at E is negative xi. So this is DLH at negative xi. And xi is, so let me just take some gamma, right? So consider some gamma of t. It's again curve such that its tangent vector corresponding to this curve is xi. Then, well, I actually need negative xi. So actually, well, some it's easy exercise if I put gamma inverse of t. It's another curve, right? If I compute take gamma inverse of t, compute its tangent vector at 0, then taking inverse coordinate-wise, like linear term in coordinates, we'll just get negative. Just get negative sign, and the other terms don't matter. So therefore, taking inverse in the tangent world corresponds to taking minus xi, right? So therefore, I can continue this. So this equals to DLH of gamma inverse of 0. Well, should be just to make it all coherent, should be like this, right? So I take the gamma inverse curve corresponding to gamma inverse and take tangent vector corresponding to this curve. So like this. Then the definition of the differential. So I need to multiply this from the left and take derivative at 0 of the resulting curve. But this is exactly, so remember I had this action, right? And this is an action, so I had this action alpha, right, from G times G to G, and well, which was GH is mapped to GH, HG inverse, right? And I have had alpha x. Well, alpha G, right? So alpha H in this case. So this is mapped from G to G, right? Which maps, well, H, G here, right, to HG inverse. So in other words, this is I'm just recalling all the notations that we had before, right? So that it's easier for you to follow. So this is the same as alpha h applied to gamma. So this is applied to gamma, and then take derivative of it, right? But this is the same as differential of alpha h applied to tangent vector corresponding to gamma, which is psi. Right? And this is by definition what is the value of the vector field vxi of h. Okay, so what do we get? We take vector field, we take some psi, we define some psi, and realized v as v psi. And so this means that this map, that it means the other inclusion, right? So every element in here is v psi for some psi, right? So therefore, every left-invariant vector field is in the image of the alpha. And so therefore we have equality, and the proposition is proved. So image coincides with exactly left-invariant vector fields on G. and this is image corresponds to action, which is multiplication from the right. You can actually, tell this story starting with action, which is action with multiplication from the left, and this will be right invariant. This is like equivalent way how to introduce this. So we have actually two ways of isomorphisms of tangent algebra to left invariant to right invariant vector fields. Okay, and so we have this corollary, which I just spelled out, which is very important to know because some people. First corollary. So vec LG is a Lie subalgebra of vec G isomorphic to G, which is tangentially algebra of the group G. Okay, here's the statement, and in many cases it's just very handy to think of Lie algebra corresponding to a Lie group as a Lie algebra of left-invariant vector fields on G. And some authors, they just define Lie algebra of a Lie group as a left-invariant vector fields on G. And now we know that this is just the same thing. Proof. So we proved almost everything except image. So V alpha is actually homomorphism of Lie algebras, right? And image of V alpha is exactly this thing, and V alpha is from G to this thing. The only thing that we need is injectivity of V alpha. So we only need to show that V alpha is injective. But we actually can see, that if I take Vx psi and compute its value at identity, I get negative psi. Indeed, how to check this? Well, just by definition, Vx psi of E is differential of alpha E of psi. And alpha E is, so I just need to take some curve, right, such that its tangent vector is psi, right, and I need to take E and apply gamma, like action by an element corresponding to this curve for small values of parameters. So gamma inverse, right? Gamma inverse. So this curve, I take tangent vector of this. E times any element is this element. So this is actually gamma inverse of prime of 0. And this we learned over there is negative psi. Right, so this was the proof of this. Okay, but this already means that V alpha is injective, because if I have some Vx psi just zero vector field, then psi, which is negative Vx psi of E, is 0. So in the kernel, so psi, again, V alpha maps psi to Vx psi, right? And in the kernel, we only have 0. So kernel of V alpha is 0. And this is why it's injective, and hence Vec L is isomorphic as a Lie algebra to the tangent Lie algebra of the group G. Okay. So next notion. So we started with the groups, right? And we constructed Lie algebras. And the first half of this semester is about relationship with of Lie groups and Lie algebras. So the question is, can you go back? Can you start with the Lie algebra, of course, finite dimensional, and construct a Lie group? And there are 3 fundamental theorems of Lie theory that actually describe relationship of such sort between Lie groups and Lie algebras. And we are on a way to answer this question. So you start with the Lie algebra, right? So how you can go back? So to go back, you need like an exponential map, and for that, well, you actually, so the path is like this. So you need to map, right, from tangent back from tangent space to Lie group, and so what's the recipe? How to construct this map? Well, we now realized Lie tangently algebra is an algebra of left-invariant vector fields, then you can take, you can take an element of tangently algebra, construct corresponding vector field, and then construct integral curve corresponding to this vector field, and this will belong already in G. And so this is an idea, and this is like an idea of construction of exponential map, which we'll discuss in the next lecture. But to prepare ourselves for that construction, we need what's called one-parametric subgroup, so definition. One-parametric subgroup of a Lie group G is it is a homomorphism of Lie groups let's call it gamma. Well, and at this point, what's important is that we talk about only real case, and we'll say something about complex case after we formulate all the relationships in Lie theory about in real case. So this being said, it's from R plus homomorphism of Lie groups to G. And I would like this to be immersion, right? Such that, so in order for this to be really one parametric, but not a constant, right? I really want this to be like kernel of D gamma is 0. Okay, and we have the following proposition about one-parametric subgroup, how they are related to left-invariant vector fields. So proposition. For any, so we have two parts in it. For any left-invariant vector field on a Lie group G, so V vec L of G, there exists unique global integral curve let's denote it gamma V, which goes from R to G. And uniqueness is given by this condition, so such that, we fix value at 0 to be E. What is global integral curve? I'll explain in a minute. So first let me formulate the second part of the proposition. So let G be tangently algebra of G. Then there exists unique one-parametric subgroup such that, well, so one-parametric subgroup of G, so this is denoted gamma x, it is from R to G, such that gamma x prime of 0 is x. Okay, so I promised to explain what is integral curve. So gamma from R to x is called integral curve. Of some vector field V on X if it satisfies the following, well, actually differential equation, right? Gamma prime of T, so tangent vector at a point T to this curve is given by vector which is given by the value of vector field V at the point gamma of T. This is for any T in R. So this is actually a differential equation that you can solve locally for any T. So locally, integral curve exists always. Right. And, well, locally means, well, so actually here I can consider some U, right, which is open, subset in R. So U is open in R. And here I should replace actually this. So this is called local integral curve, right? And they always exist. So meaning there is some U, right, for each point. V, for each point, well, P, there is integral curve going through this point, right, such that for some open U in R, this is the integral curve for this vector field. So if U is R, then our integral curve is called global. But so integral curve is called global. But the existence of this thing is not given, and the first thing is the first part of this proposition says that in this particular case, if I have left-invariant vector field on G, it has global integral curve going through zero, going through identity in G. And well, second part relates it to one-parametric subgroups. Okay, so let's prove it. We'll prove kind of both of these parts more or less simultaneously. So proof. So let, since local integral curve always exists for some fixed point, right? So we can actually consider A and B. So these are some elements from R greater than 0. B maximal such that well, we have gamma, we have integral curve going from negative a b to g, such that we have integral curve. So here should insert we have integral curve like this. So now you see it is not from R but from some interval, and this since local integral curve exists, we can guarantee existence of such A and B. And the chosen point, right through which it goes, it is well integral curve, right, such that, so our chosen point, gamma v of 0 is identity, right? So 0 is inside here, and we would like value of gamma v of 0 to be identity. What's important is that local curve exists and unique. So and unique if we fix a value at a point. All this is I take as a prerequisite from differential geometry, so I'm going to use it. Okay, so let's consider 2 points, C and S. They are inside this so these are 2 real numbers inside this interval, such that their sum is also in this interval. And consider 2 curves. So alpha of t is gamma v of s. So this is curve of t. Well, we can kind of vary t and fix s. Gamma v of t, and bit of t is gamma v of s plus t. So our goal is to show that alpha and beta coincide. That is, gamma v behaves as one parametric subgroup, at least for those t and s that live inside this interval. And then we will say that, use this to say that actually a and b are infinity. And this will be the end of the proof. So okay, how to prove that alpha coincides with beta? We actually would like to use this uniqueness. So I have actually alpha of 0 and beta of 0. They coincide, and it's gamma, well, just from definition, gamma v of s, right? And both alpha of t and beta of t are integral curves. Integral curves of v, right? Well, of course, this is integral curve of what, right? So we in the beginning, the proposition says that for any v, we have integral curve, right? So we fix the logic of proof is that we fix this v in vec LG, and then this is integral curve of v. So there are integral curves of v with the same value at 0. Then they coincide. So we just need to justify why they both integral curves of v. For beta, it is immediately follows. So beta is integral curve. So indeed, beta is integral curve. This follows immediately from the fact that gamma v is integral curve. And for alpha, well, we need to compute something, right? We would like to see that d, so we would like to take d, gamma s, gamma vs, gamma v of t, right, dt, right, which is, well, tangent space, tangent vector of this curve as a curve with parameter t, right, at the point t. This is what it is. This is what it stands for. Well, this we kind of don't fix the point t where we take this tangent, and this will be yeah. So this will be like a function of t. So what it is? Well, I take this point, multiply from the left, and take derivative. This is by definition differentiation. This is differential of left multiplication by gamma v of s applied to this tangent vector gamma v of t over dt. Okay, so where are we? Right, we're computing this. And now we're using the fact that this is integral curve. Therefore, d gamma v of this by dt is actually v of gamma of t. Right? This is the fact that we're using. So we continue. And we have dl gamma v of s, and then v of gamma of t. Right? Then we use left invariance of v, right? And this, so by left invariance can be read out as follows. Is that this is the same as v at different point obtained by multiplying this by this from the left. And v here. And you see what we got. We got exactly the condition for this thing that is alpha being integral curve compared to this. So this equals to this. Should compare to this condition for alpha to be integral curve. So both alpha and beta integral curves, their value at zero coincide, so therefore they coincide by uniqueness of local integral curves. And it is left to prove for both parts of the proposition, right? We actually, no, okay, so, right, so we actually need to prove, so maybe let's use, so we need to prove that A and B are infinity. So we need to prove that A and B are infinity. Then actually our integral curve gamma v will be global integral curve as needed in part 1 of the proposition. And also this global integral curve is one-parametric subgroup as needed in part 2 of proposition. Also, there was some condition in part 2 that we're going to check. All right. So suppose that B, for the sake of contradiction, is finite. So suppose that B is finite. Then there exists actually, so we can actually then fix some positive C, right, which will be responsible for shift of this interval a little bit to the right. So such that, but a little bit so that the shift intersects with the initial interval. So in formulas it means that negative A plus C, B plus C intersect A, negative AB is not empty. And put, so define another curve, gamma v tilde of t, which is gamma v of c, gamma v of t minus c. So this is constant, so this is really, sorry, again, gamma here, gamma v, and gamma v here. Okay, and so actually you see this shift here, right? And so because of this shift, gamma v tilde of t is integral curve is integral curve of v at this shifted interval, negative a plus c, b plus c, right? Because this shift kills this shift, and since this is integral curve there, well, this is just some constant, right? Renormalization, which is spit out of both sides of the condition of this differential equation, which is condition on being an integral curve. So this is an integral curve, easy to see, and on the intersection, so meaning that minus a plus c, b plus c intersect negative a, b, gamma tilde of v and gamma tilde of and gamma v t, they coincide. Just this is because, let's see, so if t is an intersection, then t is in here, right? And gamma of t minus c, right? Then both, okay, so then this and this, they are both, and their sum is in negative ab, right? So indeed, on intersection, c, t minus c, and c plus t minus c, they're all, right, they are all in this interval, where we know that this thing behaves as a homomorphism of groups. So therefore gamma v of c, gamma v of t minus c is gamma v, again, gamma here, of c plus t minus c of t. And so therefore they coincide. So gamma tilde of t is integral curve on one interval, which is shifted a little bit. Gamma t integral curve on the initial interval, they coincide. So therefore, we constructed the integral curve on union, right? So we have integral curve on union, which is negative a b plus c. So then actually b is not maximal, as we assumed in the beginning, and therefore it's a contradiction. So b is not maximal, which is contradiction. So therefore, our assumption that b was finite is not true, so b is infinity. And in a similar fashion, so similarly, you can prove that a is infinity. So this means that indeed our left-invariant vector field V admits global integral curve. So we proved part 1. And this global integral curve, moreover, is one-parametric subgroup. So to prove part 2, we only need to prove. So what was? So recall part 2. So there exists unique one-parametric subgroup gamma x from R to G such that gamma prime of 0 is x. Okay, so maybe I didn't write everything that I wanted from this proposition. So I would like to add that moreover, and this is important for me, my gamma of x that I would like to see here is exactly this gamma global integral curve that I found in part 1, so this one, right? Gamma v is just gamma v x, right? So x is an element, so for any x from G, right? X is an element in G. There's this unique one-parametric subgroup gamma x, such that its tangent vector at 0 is x, and moreover, it coincides with the global integral curve for a left-invariant field defined by this x, right? Remember this map from G to left-invariant vector fields. So xi to v xi. So this is exactly notation from this construction, right? X define left-invariant vector field Vx, right? And by part 1 we have gamma Vx, which is exactly one-parametric subgroup that part 2 gives us. So let's see how to prove of part 2. We almost did everything, right? Just need to, so existence, so we have gamma v, right? So existence. So we just put, so existence of gamma x. Gamma x to be gamma of Vx. Exactly like in this equality, right? So there exists one-parametric subgroup gamma x. So we just define it to be this one because we know what is this right-hand side. I just explained it, what it is. And uniqueness is that any gamma x from R to G, one-parametric subgroup so to G, sorry, here. One-parametric subgroup, any other one-parametric subgroup, such that, well, this property, that gamma prime of 0 is x, is integral curve for v minus x. Right, this is left-invariant vector field whose tangent space, whose tangent vector at 0 is actually x. Okay, so from this statement, uniqueness follows, right? So you take any other one-parametric subgroup with these properties, then first of all, gamma of 0, gamma tilde of x at 0 is E, just because it's a Lie group homomorphism, so 0 should go to E. So this value is fixed, and it's integral curve. So therefore, it should coincide with the one that we found when we proved existence, right? But why any one-parametric subgroup is an integral curve with such properties, an integral curve for this? Okay, so this is just some check. So what we need to do? We need gamma x tilde of t plus s d over ds. So this thing at s equals 0. At s equals 0, yes. So this is what? On one hand, this is gamma x tilde prime of t. Then I use that this is a homomorphism, so therefore it is d over ds at s equals 0, gamma x tilde of t, gamma x tilde of s, right? Well, this is then dl gamma of t gamma tilde x of t gamma tilde x of s, well, prime of 0, like this. So gamma tilde of x at 0 is x, right? So this is d L gamma x of t of x and okay, so this is exactly the value of v minus x at point, well, gamma x of t. Because, well, you take, so this is left invariant vector field corresponding to, well, minus here just for some technical reasons because of this. I tried to explain it over the lecture, right? But really, that v negative x at 0, right? Its tangent, it's the corresponding, its value at 0 corresponds to actually to x, right? And it is left invariant, so therefore, how do I obtain its value at gamma x of t? I will just take its value at 0 and move it using left translations to the point gamma x of t. So this is actually it. And what we get is that, well, gamma x tilde prime of t is exactly this, and this means that gamma x tilde is integral curve for v minus x. So all one-parametric subgroups with this property, they're all integral curves of the same vector field, which at 0 they have value e, and so they all coincide, and therefore uniqueness follows out of that. Okay, and so we proved proposition, and maybe even more than was originally stated. So we have this part, which really just comes from the proof itself. We didn't work too much to get it. And so, yeah, okay, we got the proposition. I think it's a good place to stop.